This is a brief introduction to the error correction model. In econometrics, we have a whole collection of models that can actually be called error correction models. And this lecture will introduce a very simple such model, which will illustrate the basic ideas behind all of these error correction models. So the error correction model is a dynamic time series model. It has similarities to the partial adjustment model, but it's not the same. So let's look at the setup for the error correction model. We have time series data on a dependent variable, and let's limit ourselves to just a single explanatory variable, x. We have the same case as the partial adjustment model, that yt is affected by xt, but if there is a change in xt, the full effect is not experienced in this period. It takes some time for yt to adjust to the change in xt. And there are many reasons for this, like technology, information, and so on. But according to this model, there is some lag. It takes some time for yt to adjust to changes in xt. So we introduce this yt star, a latent unobserved variable, which is the value that yt would take if the economy was without frictions of any kind. That is, if all adjustments could take place instantaneously. So here is a simple example of an error correction model. We model the latent variable yt star as a linear regression model depending on this xt, and we have the nu-t, the error process. We think about this as the long-run relationship. And the idea here is that if there's a change in x, y will change. It will take some time to adjust, but eventually it will change. So in the long run, there is a relationship, contemporaneous relationship between yt star and xt. The particular adjustment process is what differs between the error correction model and the partial adjustment model. In the error correction model, a simple example of an adjustment process can look like this. On the left hand side, yt minus 1, we have the actual increase in y. This is the increase from the previous period to this current period in the dependent variable. Now, in the error correction model, think of yt star as the equilibrium value of yt, the value that yt would have if the whole process or the economy was in equilibrium. So the first parenthesis is the deviation from equilibrium. Yt minus 1 is the actual value of y in the previous period. Yt minus 1 star is the value in the previous period in equilibrium. So the first parenthesis on the right hand side, you can simply think of this as the error in the previous period. The error in the terms of the deviation from equilibrium. What the error correction model says is that the actual change in y will respond to the error, the deviation from equilibrium. To consider a concrete example, let's say that yt minus 1 is 100. That was the value of y, the actual value of y in the previous period. Let's say that the equilibrium value in the previous period was 105. Yt minus star was 105. Then the first parenthesis would be 5 units. We are 5 units below the equilibrium value in the previous period. The error correction model then says that that will imply a change in y in this period, but there will only be a partial change. If lambda, for example, is 0.4, then we would make a 40% adjustment of these 5 units that was the error in the previous period. So there would be an increase in y in this period by 0.4 times 5, or 2 units. So the process will slowly move towards equilibrium. But the deviation from the equilibrium is not the only part that affects the change in y. The second part that will affect the change in y is the change in the x variable. So the second parenthesis is the increase in the x variable. And according to the error correction model, yt will also respond to a change in the xt variable. For example, if there is an increase in the x variable by, let's say, 5 units and phi is 10 units, then there will be an increase in the y variable of 10 times 5, or 50 units. Finally, according to the error correction model, the total adjustment, the total change in y, is the sum of these two effects. So the error correction model is the combination of these two equations, where again this is unobserved, but if I plug it in here in the adjustment process, I get that yt, I can move this over on the other side, yt minus 1 plus lambda theta 1 plus theta 2 xt plus nu t, that's yt minus 1 star. Take that minus the actual value in the previous period plus phi xt minus 1. Let's expand both parentheses. This is yt minus 1 plus lambda theta 1 lambda theta 2 xt lambda nu t lambda yt minus 1 phi xt minus phi xt minus 1. So let's combine the terms. We have a constant here, lambda theta 1. If we look at xt terms, we have them here and here. So we have plus lambda theta 2 plus phi xt. We have lagged xt's here, so minus phi xt minus 1. And we have lag dependent variables here and here, so plus 1 minus lambda yt minus 1, and we're left with the error terms, nu t. Now I want to make this into an ADL model, so let's just rename some of the parameters. So we'll just rename this beta 1, we'll rename this beta 2, we can rename this minus phi to theta. Well, let's not do that because we already have theta, so let's rename it something else, perhaps gamma. And we rename 1 minus lambda rho, and the error terms, lambda nu t, is renamed to epsilon t. So we can clearly see that it's an ADL process. Yt is beta 1 plus beta 2 xt plus gamma xt minus 1 plus rho yt minus 1 plus epsilon t. So we see that this is an ADL model. We have one lag on the y variable, so it's 1 here. We have one lag on the x variable, so it's 1 here. The error correction model is an ADL 1, 1 model. Typically, the most important parameter in the error correction model is the speed of adjustment, the lambda. But we can easily see that Once I have row, I can easily get lambda as 1 minus row. And I can get all the other parameters of the original error correction model from the newly introduced parameters in the ADL model. So just to state what we did, if we combine these two equations, we get this ADL model. The relationship between rho and lambda is that the rho is 1 minus lambda, or lambda is 1 minus rho. And the error correction model is an ADL 1,1 process. Again, under reasonable assumptions on the error term, most importantly that they are not autocorrelated, we can estimate this ADL 1,1 model using simple OLS. That will give me consistent but not unbiased estimates of all the parameters, beta 1, beta 2, rho, and gamma. And from these parameters, I can get the parameters of the error correction model. So I can estimate the speed of adjustment, lambda. I can estimate the y parameter, that is the effect that the change in x has on the change in y.